Thank you. Thanks everyone for being here, and thank you to the organizers for having this conference. So just to begin, go through some notation and tools for these PDEs. Now talk a bit about the problem and give a short, quick proof of the main theorem. So just the standard notation is we have a derivative. We have it multiplied by 1 over I. Omega is going to be a bounded open subset of RD with smooth boundary. We have these Sobolev spaces. This tilde here, I'll explain in a second, but really what it means is the supportive U is going to be contained in the closure omega. And since omega is smooth, we have a characterization of it, is that the tilde space is the dual to WSP, which is nice. The other nice part is this decomposition. So if you decompose S to its integer and fractional part, you can write anything in the dual as the sum of K derivatives of WRP function, which is handy. We'll explain that later. We have the standard Fourier transform. We have dual pairing between spaces in the dual. And then we have this bracket notation as well. So for the polyharmonic operator, and at least for these inverse problems, we're going to look at two operators, LK, where the principal part's this negative Laplacian raised to an integer m. M here is going to be bigger than or equal to 2. And then we have this perturbation, this Q dot D, and this little q. Little q you can think of as potential, but I'll just call these coefficients for now. For a solution, LU equals 0, we can define this set of data. We call this Cauchy data. There's many choices, but we just selected one. And then you can define the Cauchy data of the entire operator as the set of all Cauchy data for all solutions. What we would like to do is to show that if we know information of the Cauchy data, then we can obtain information about our coefficients. So this is the inverse part of the problem. Instead of given the coefficients, we want to, recover them given the Cauchy data of the operator. So some history of this. Krupchak, Lasses, and Ullmann, they first worked with bounded terms, i.e. Q is going to be bounded, and capital Q's have one derivative, but also be bounded. Then they started working with unbounded potentials, at least for the little q. And they also did some work in partial data of the boundary. So not having all of the information needed. And then Esselbekov started working into the study of regularity. So instead of just being bounded, you can actually have negative order Sobolev space, so negative order derivatives. And then Esselbekov with Ayer. Once again, they actually lowered, they had the same order for regularity, but they had a more general P. And then Brown, my advisor, and myself, we further reduced regularity from the originals paper. So my paper is on the archive currently. The main theorem here is if we have two operators as defined before, LK, and we have S being less than M over 2 plus 1, and P and S satisfy these inequalities. And if we have the coefficients of these spaces, then the Cauchy data of the operators, if we know the information about the Cauchy data, then we actually get that our coefficients are equal. And here, the important part is S. So our condition was S being less than M over 2 plus 1. The previous best case scenario was S being less than M over 2. So we were able to increase S by a power of 1. So this, what we need is why the reason we can't have S to be larger is we're going to need to study some limiting behavior of solutions, and this S is going to pop up. So to start, we're going to create and construct solutions. So we're going to construct complex geometric object solutions. and of the equation LU equals 0. And we're going to want these solutions to have this form. Here, zeta is going to be a complex vector such that mu1 and mu2 are real vectors, and they are perpendicular to each other, but also unit. And h here is going to be a small parameter that is going to be the limiting parameter. We're also going to have some requirements like a to be smooth. So you can think of this a as the amplitude, psi as the remainder. In general, we're going to have either a to be 1 or x dot zeta. In either case, something that's important is a is bounded, at least on the closure of omega. So what we can do now is plug in our CGO solution into the PDE, and then we conjugate, we left multiply by h to the 2m e to the minus x dot zeta over h. What this does is it cancels out the other exponential, and we're left with looking at an equation like this. Here, f, I'm not going to describe right away. You can see f here is going to have q, little q, capital Q, and a's. That's where it's dependence. What do I want to know is, given an a, can I solve my left-hand side for psi? Here, P of HD is just this conjugated Laplacian. This is So right now we switched our goal, and we're going to solve this equation for psi. To do so, we're going to want to work with function spaces that kind of play well with our operator P of HD. So P of HD has symbol here under the Fourier transform. And what we're going to do is use function spaces and that work well with our operator. The idea of using spaces based on a symbol of an operator is due to Bourgain, and the spaces we use were developed by Haberman and Tataru for the study of the inverse conductivity problem. So for a given real number lambda, we can define x lambda to be the following. The important part here is it has this norm. So you can see that this norm has dependence on our symbol. What else you can see is we perturb it just by h, and what this does is it can grant us integrability, in which case sometimes lambda is negative, and if P of h c is 0, then you have a 1 over h instead of being unbounded. So we perturb by h to give us integrability in case we are near 0. So our next thing is, we can think that if we find a right inverse to this, if we can find a right inverse and solve this equation, then if we apply P of HD m to both sides, we actually get an equation to our solution, which gives us what we want. So our goal now is to construct a right inverse. So what we do is we just take a smooth, compactly supported function that's 1 on the closure of omega, and define this. Now, to be invertible, you also need to know what spaces you're working with. So for any lambda, I sub phi is a bounded operator from x lambda to x lambda plus 1, and is a right inverse to P of HD. What this does is, instead of looking at this equation, we can now transform this into an integral equation here. Once again, we can rewrite this as basically I plus an operator that you apply psi to the left-hand side. So if we can show this side is small, we can show it has a solution. What I mean is, if I can show this part is an operator between xm over 2 to xm over 2 is less than 1, then we can construct this Neumann series so we know the inverse is bounded, or it exists and it is bounded. So to do so, we need to bound these two operators in this xm over 2 space. Before we go there, we're going to use the Sobolev embedding theorem for negative order Sobolev spaces. So if S and P are defined as before, and little q and capital Q are in the same spaces, then since P is bigger than or equal to 2, we can lower the order, or we can lower the power to down to 2, since omega's bounded, and we can increase the number of derivatives, which increases the power p. Here, p prime is going to be bigger than d over r. Written like this, and r once again is going to be the fractional part. What else is nice is that since we have this decomposition, that q now is m derivatives of a WRP function, and WRP and p has this inequality, we actually get that as Helder continuous. So we can think of these q's as m derivatives of a Helder function, which will be nice. What else is going to be useful is knowing how these these Sobolev spaces and these X lambda spaces interact, and in this case embed. So we can think of as under the Fourier transform, derivatives turn to just Cassi. So if we have Cassi to the S and we have our symbol here, if we take the supremum over all Cassi, we actually get a uniform bound just dependent on H and the dimension. The important part here is powers of H. In inverse problems, especially the ones I do, we're just trying to find powers of H. So what this tells us is, in fact, that if U is in X lambda, it's also in WS2. And it has the following inequality. So we do pick up exactly what we saw here. So this part is the important part. So since we know this inequality, the adjoint inequality equality works as well. Now this is a technical proposition. So this previous lemma was when Q was in W minus S2. This one is when you are M derivatives of a Helder function. This last line is the most important. If we are, so F here is C theta, so it's a Helder continuous function. We take alpha derivatives of a Helder function, and we see this operator pop up in our PDE. So beta here is either 0 or 1. Then this operator is going to be bounded by this. And what's nice is, instead of just being bounded, since we're Helder, we get a positive power h to the theta, more h's than we originally had. So that was nice. Having positive powers of h is a good thing. So now, as we saw, we need to bound these two terms. This first one, since I phi is a bounded operator, we get to here. Since Q was M derivatives of a Helder function, we can rewrite it like this and use the previous lemma to get this. So we have h to the theta r. Same thing for this following one. And now, since h was just a number less than 1, we can also find an h small enough such that this operator is less than 1. So given h small enough, we have a solution psi that satisfies this following bound. Now, as I said before, that F is going to involve little q and capital Q. And we have this previous lemma that shows us that this x minus m over 2 will embed into this our Sobolev space. The issue, though, is we don't get an estimate that's good enough to improve results. So the issue here is we fixed a zeta, and as you know, this norm isn't dependent on this zeta. So instead of just fixing a zeta, we're going to actually average over a class. So what we do is, given any C and RD, we can find disjoint vectors that are also disjoint from each other in unit. We can rotate those vectors in their own plane, so you still are perpendicular to C naught and to each other. And you can find specific zeta to be the following. The nice part about these two zetas, if you add them together, the first two terms disappear, and you're just left with minus IH C naught. And if you limit H to 0, the last term disappears, and it just turns to something like mu1 theta plus mu2 theta, as we saw before. So these are in a similar form to what we first started with. And here's the theorem. If we average our norm over all choices of zeta, where here h is going to range from h to 2h, or s is going to range from h to 2h, and our theta, the rotation, is going to go from 0 to 2 pi, we get this. Now the difference here is before we would have s plus m over 2, or t plus m over 2, and now we're actually get an extra power. We have a -1 plus epsilon. It's a negative here. What's happening is we're basically getting an entire h in the numerator more than we previously expected, and this allowed us to improve the result. So since the average is small, what we can do is we can find a zeta that will fix an h and theta such that this is true. So for a fixed correct choice of zeta, we have the following estimate. But we're going to run into an issue. But first, so given f to be the right-hand side of our equation to be this, we have psi has this estimate, which is nice. But as I said before, h was a limiting factor, and now in this part, I fix my h, so I can't limit it. So that's the issue. How we get around that is by we use sequences. So we're going to have we're going to have a sequence hj going to 0, each one corresponding to a correct zeta, which will denote zeta j, and then each one would also have the rotation. And now since theta j is a bounded sequence, passing to a subsequence, we can assume it's convergent. And so for k can be 1 or 2, which is just going to depend on your either zeta 1 or zeta 2 as before. And j is going to depend on this hj, it's the sequence. So for each h fixed j, we can find a solution psi j with this bound, and q, little q and capital Q satisfied this bound. So in either case, we added a power of h to every, 0.1 power of h to every bound. What we do now is instead of using the Cauchy data, we use bilinear forms. B0 here is just a bilinear form for a polyharmonic operator. Given a set of Cauchy data, you can find a bilinear form for it. And then these two are just the dual pairings. What's nice is if the Cauchy data of both operators are the same, then we get that B1 is equal to B2 with some assumptions. So once again, here's my main theorem, and I'll do a really quick proof. Without loss of generality, I can just, since s is less than m over 2 plus 1, I can write s like this for epsilon small. We first show q1 is equal to q2. Through this technical lemma, what we can do is we can find psi jk, a sequence of solutions, and we know u1 and u2 are going to have CGO forms. We plug u1 and u2 into our form, and we know since they're equal, it has to equal 0. We limit j to infinity, or hj going to 0, and we get this following equality. What's nice here is this kind of looks like the Fourier transform of q1 minus q2. Once again, since there's this rotation, we just divide by e to the I theta, which undoes that. We use the other choice of zeta, and we're able to actually, and plug in a1 and a2 both to be 1. And we get that a vector dotted with the difference is 0 if mu and c naught are 0. So if they're perpendicular. This gives us that the curl is 0, which means we can, since omega is a ball, that we can set them q1 minus q2 to be a derivative of g. Now we run through this whole argument again, now with a1 to be 1 and a2 to be something like x dot zeta. We plug it back into the bilinear form, we send hj to 0 again, and we get that G is 0, which tells us Q1 equals Q2 as we wanted. Now for my last slide, just to show Q1 is equal to Q2, instead of multiplying by H here, we plug in U1 and U2, the forms of the CGO solution, send J to infinity, and it immediately pops out that Q1 is equal to Q2. So here are some references. And are there any questions? And thank you for coming to my talk.